Okay, morning guys. Can you hear me? Janice, can you hear me?
Yes, sir.
Okay, so let me see how many of us. So we are missing two. Let me share the screen. So today we'll just do a revision. Okay, revision of the last two topics that we have done before the holidays. So we will try to finish this today, and then plus very simple worksheet. Okay, so that we can conclude today's lesson. Yeah. So I will share the screen. So it will be more towards our discussion over here. So I want you to also discuss, participate as well while I'm teaching you over here. So when we do here, when we look over here, okay, benzene and its compound, okay, we can actually see that, okay, benzene, okay, benzene having this structure. So I'll just draw this structure. So C6H6, okay. So this benzene, okay, they can actually go through certain reactions, okay, and these reactions, okay, basically they are three types of reactions, okay. So if I write down over here, okay, there are three types of reactions, okay. So let's actually look at the three types of the reactions that C6H6 can undergo, okay. Not only C6H6, okay, maybe when we look at something that has benzene, what are the reactions that we actually look into? But the main reaction that we need to look into is going to be the main one, okay, because the delocalized electrons, okay, there are delocalized electrons over here, okay, in the circle over there. So because of the delocalized electrons over there, so Gabriela, Nicole, nucleophile are attracted to those circle or those delocalized electron, or is it going to be electrophile going to be attracted over there? So which one?
The electrophile, is it?
Yes, electrophile, okay, are electron loving. So there are a lot of electrons over there. So we know that electrophile are attracted over there, and this is going to be electrophilic, the mechanism of the reaction. Yeah, the mechanism of the reaction is going to be electrophilic substitution. Okay, so we are going to learn about, we actually already learned, okay, we already learned about this mechanism, electrophilic substitution. Apart from electrophilic substitution, there are two more reactions, okay, that we learn, which is going to be, one is going to be if you have methyl benzene, okay, if you have methyl benzene, you can have this reaction, free radical substitution. We have learned this before, okay, free radical substitution. And we also have this situation whenever you have methyl benzene. So whenever you have benzene, you are going to get electrophilic substitution. But if you have methyl benzene and so on, you are going to actually get free radical substitution, as well as another one, which is going to be oxidation reaction. So I think the number 2 and number 3 are the one that students will tend to forget. Okay, so the free radical substitution and oxidation reaction. So if you look at these reactions, yeah. So here, okay, let me check also the attendance. Okay, hold on. Now, still missing, yeah. Hold on. So 11 minus 2, so it's 9. So 9, so we're supposed to have 11. So 2% missing. Shane, are you here? Shane is not here. Who else? Can you see who else missing? Okay, Shane just joined. Nicole, Risha is here. Gabriela, Nicole is here. Arnetta is here. Victoria is here. Lavi, is Lavi there? Oh, Lavi is here. Okay, Janice is missing. I thought Janice was here just now. Maybe connection issues here. Okay. So anyway, we'll continue. Okay. So here, okay, when you look at these reactions involving benzene, okay, so Janice is joining. So whenever you have benzene, okay, when you are reacting with Cl2 and Br2, if you want the Cl2 Cl to go into to be substituted to this position, any of this position over here, what you need halogen carriers. Okay, so if you are using Cl2, you are going to use a catalyst which is going to be FeCl3, or you can actually use AlCl3. These are halogen carriers. If you are using Br2, if you want to substitute using Br2, you have to use FeBr3. But basically, what are their functions? They are going to be catalysts or going to be known as halogen carriers. They are going to carry this halogen, Cl and Br, and they are going to put it substitute them, okay, in the benzene ring over there. So the condition, so what is the condition required for this? Victoria, is there any specific condition that you require for benzene reacting with Cl2 and Br2, or is it room temperature? Do you need to heat? Do you need to reflux? Charlton, you can quickly refer to your textbook, okay, to answer these questions. So we just want to review only. So what do we do? Is it supposed to be at room temperature, or do we do heating?
I forget.
Try. Where's your textbook? Look. Look at page 384. Justin, any idea? Do we need to heat this?
No.
Yeah, no need. Okay. So this one, I think very important to identify as well. It's okay to forget, okay, but I think now we need to actually refresh our memory on this, okay. So in order to do this, basically we just need the halogen carrier, and you just need to have do this under room temperature is fine already. So you do not need to heat them up, okay. So room temperature, and then the catalyst over there. So if you like, for example, okay, if we are going to use this reaction and then you want to put Br, yeah, the Br will go in. But there will be some situations where we are going to, if we are going to use methyl benzene, okay, and we are going to use the react with the Cl2, and then we put the halogen carriers and so on. So what do we expect to see? What we expect to see is, okay, we are going to get a mixture of product, okay, because this is going to be CH3 is an electron. Jody, is it electron donating group, or is it electron withdrawing group? CH3.
Donating.
Yeah, so electron donating. So I'll just put it over here. CH3 is the electron donating. So if it is electron donating, so this will actually activate certain positions. Okay. So Nicole, Trisha, do you remember what are the positions that electron donating group will activate?
I forgot, sir.
Okay, please remember, it's okay to forget. Okay, it's okay to forget. But now I think please recall, by the end of today's lesson, you must remember everything. Yeah, that's the reason why I'm doing this lesson today. So it is going to be 2, 4, 6 activating. Okay, 2, 4, 6 activating. So in this case, we are going to actually have, okay, the Cl. Okay, the Cl can come over here, CH3. So this is position number 1. So this is going to be position number 2. Cl will come here. Or you can actually have CH3 over here. And then at position 2, 3, 4. Okay, Cl will come over here. You do not need to draw for 6 because it's the same as the first one over here. It's the same. So this one, if you can refer all this in your textbook, okay, you are going to get 2HCl. This reaction is going to happen. You are going to get a mixture of product. But this is not what I want to actually highlight over here, because I want to highlight what are the differences that we are going to have. Like, for example, if you have methyl benzene and I'm going to use Cl2, but the Cl2 is going to be different. The Cl2 is going to be in excess. So if it is in excess, how is it going to affect? So the way it is going to have effect is going to be still a mixture, okay, still a mixture, but you are going to get a different mixture. It's going to be a combination of 2, 4, 6. So it's going to be, you are going to get the CH3, Cl will come over here. And then you are going to get another Cl over here. This is going to be under excess. And you can actually also have CH3 here. And you can have the 2 and 6. So this is going to be Cl and Cl here. And you can also have combination of everything. Cl here, Cl here, Cl here. And of course, okay, if you want to actually put it over here, plus HCl, how many HCl that you are going to get, that is going to be, depends on how many you substituted. In this case, 1, 2, 3, 4, 5, 6, 7. So that's going to be 7 HCl here. Okay, so this one, if you want to actually write down in full, yeah, and you want to balance, then you have to balance accordingly. Okay, so anyway, we are not interested in that. Okay, what I want to actually highlight over here is when you have Cl2 in excess, you are going to get combinations. Okay, combination in form of position 2 and 4, position 2 and 6, and position 2, 4, 6. Okay, that is going to be the situation over here. Now, if you have, okay, another situation that is going to happen, if you are going to have a situation whereby, okay, we have done electrophilic substitution, we are going to just discuss a little bit on this free radical substitution. Now, for the free radical substitution, what is going to happen is when you have this Cl2 under the presence of UV light, okay, which is sunlight, okay, and you actually boil methyl benzene. Okay, we do not actually have free radical substitution happening with benzene. Okay, so benzene, if you want to have the Cl to go into the benzene, you need catalysts, you need halogen carriers. But in this case, there are no halogen carriers. So it means now we are just going to have free radical substitution. So how the free radical substitution actually works? So basically, it works, I think you need to actually know about the mechanism of the reaction: initiation, propagation, and termination. Okay, that is very important. But now, okay, what is going to happen? Basically, you are going to get a mixture of products. Okay, so if I draw here, you are going to get CH2, maybe Cl come over here and give you HCl. But what will happen if the reaction continues? Okay, if you have excess Cl2, the reaction is going to continue until all the hydrogen that you have in the side chain to be completely substituted. It means you are going to have, okay, CCl3, and then you have a benzene over here. This is going to happen if it is the reaction is going to be completed. Okay, so this is going to be some of the things that we need to take note over here. So there are, like for example, if you have this benzene reacting with Cl2 and you have these reactions, but when you have CH3, for example, methyl groups attached to it, you can actually have different combinations. Okay, hold on for a while. Yeah. Okay. So you need to actually understand, okay, what is going to happen here. That is actually very important. Okay, free radical substitution. Okay, the same conditions and everything is going to work. Okay, but the important or the difference over here is this part, which is going to be, this must be in boiling. So it means the methyl benzene that you use, okay, must be boiled. So generally when you use free radical substitution, we just use sunlight or UV light. That's it. The reaction will happen. But in this case, it's going to be boiling. So do all the reaction before the boiling UV light reaction need halogen carriers? Okay, let me actually try to understand the question. Do all the reactions before the boiling UV light reaction need halogen carriers? You mean don't or do? Justin? Do. So basically it's like this. Um, Halogen carriers are required whenever you are trying to put any halogen into here. It means into the benzene over there. So that is going to be the requirement. You need halogen carriers. But when we are talking about free radical substitution, okay, so we are going to actually put the halogen not into the ring. So it will be like something like CH3. So we are going to replace the hydrogen over here. So without the halogen carriers, okay, we cannot actually have the Cl entering over here. So that's why only free radical substitution is going to happen. So do the Cl and the Cl excess, do they need halogen carriers? Yes, they do need halogen carriers, Justin. So it means in this case, okay, the question is, when you have this Cl2 and excess over here, the Cl, the moment they are entering the ring, okay, it means the moment they are entering the ring, you need to have halogen carriers, must. You need to have halogen carriers. But okay, whenever we are talking about this free radical substitution, you do not need any halogen carriers. I hope that that is clear, right? Is that okay, Justin? Okay. Now, so the next part that I want to actually teach over here, but before I forget that, I want to highlight this again. Okay, do remember, okay, free radical substitution when it comes to benzene, because benzene is generally quite unreactive here. So if you want to actually react, okay, in this case, you need to boil. Okay, you need to actually the free radical substitution for methyl benzene or any kind. It doesn't only happen for methyl benzene. It happens for any kind of alkyl groups being attached to the benzene. So it means if you have, like, for example, okay, if I erase this part, and then if I have a benzene being added with this CH3, CH2, CH3, for example, okay, free radical substitution can still happen over here. Okay, the Cl can actually go. And if you ask me where it goes, I think that is going to be more towards your AS knowledge. Yeah, where it goes and how it's going to form, you can read further. Okay, but again, okay, it is not limited only for methyl benzene. It is for any alkyl benzene. Okay, even if you have the Cl over here also, like for example, I just give you additional information. If you have CH2Cl, for example, can we have free radical substitution? Yes, you can, because the moment you have the hydrogen and hydrogen over here, free radical substitution can still happen. Yep. But you must make sure that they have boiling. Okay, it means whatever benzene the alkyl benzene that you use, you must be it must be boiling, and then you must have UV light. That is very important. UV light so that you can get the free radical. Okay, let me actually continue. Let me move on. The second part that I would like to talk about is going to be when you are going to look into nitration reaction. Nitration reaction is going to be done with 50% HNO3 and 50% H2SO4. So they call nitrating mixture. Okay, so it is going to be reflux at 55 degrees Celsius. That's going to be the condition. Okay, so in this case, do we need any halogen carriers over here? Okay, this one, okay, you do not need any halogen carriers. Why? Because the NO2 plus, okay, the electrophile that you are going to actually produce over here is going to be very, very strong. If they are very strong, they are not going to require any halogen carriers or any kind of catalyst over here. I think it's enough. Okay, when we say catalyst, maybe you can say the catalyst is going to be acid concentrated H2SO4. Okay, because without the acid, the reaction will not happen. Okay, so anyway, what's going to happen is going to be you need to know how to write the equations for the electrophile. Okay, so in this case, like for example, if I have HNO3 and I have this concentrated H2SO4, how am I going to get this NO2 plus? So they are going to get NO2 plus. You are going to have H3O plus, and you are going to get HSO4, HSO4 minus over here. So I think it's not balanced. You just need to put 2 here, and you just need to put I think 2 here. Okay, I think it will be balanced, but you can always check from your book. Okay, but the important thing over here, you are going to generate this. Okay, you are going to generate this electrophile. Now once you have this electrophile, okay, okay, once you have this electrophile, then the reaction can happen. So in this case, like for example, if you have a benzene, okay, and you are going to have like NO2 plus over here. Okay, so you need to know about the mechanism of the reaction. You can actually go through my previous notes and so on. So what's going to happen, you are going to get this nitrobenzene, NO2. Okay, now so when you have this NO2, of course you are going to get, because it's a substitution reaction. Yeah, please remember it's a substitution reaction. So if you just put like this, then there will be H plus is going to be given. Okay, but if you want to write the mechanism of the reaction, then it's going to be different. Yeah, so the mechanism and so on, the diagrams, everything is in my previous video, and it is also in my in your textbook as well. You can actually check on that. Okay, but I'm interested with the further nitration. Okay, so what will happen, okay, if you do further nitration? Okay, it means the you still continue the nitration. So the further nitration is going to be like similar to what we have discussed over here, the combination. Yeah, they are going to give you a combination. So the combination that you're going to get over here is going to be 1 3, okay, 1 3 and 1 3 5. Now why 1 3 and 1 3 5? Like for example, if you have this nitrobenzene, I want to actually do further reaction. It means I'm going to actually nitrate it more, okay, where this NO2 will come in. So they will come in position number because this is 1, yeah, position number 1. So they will go into position number 3. So it means if I draw over here, they are going to go NO2 here. So they are going to come over here, NO2. So this is 1 3. And you are going to have, if there is further nitration, you are going to get 1 3 5.
1 3 5.
Now, so can you actually tell me, okay, so this is 1 2 3 4 5. So this is going to be NO2 over here. Now, But again, do remember this one, you need to be very careful when you write down. So nitrogen. Okay. So here, okay, this is going to be 135, okay, trinitrobenzene. You can check from your textbook. But what is the reason, Charlton? What is the reason behind, okay, this NO2 going into position number 3 and this going into position number 3 and 5? What is the reason, Charlton?
Because electron withdrawing.
Yes. Which one is the electron withdrawing?
NO2.
Yeah.
Plus.
So this NO2 is electron withdrawing group. So when they are electron withdrawing group, they are going to actually activate position number 1, 3, and 5. Okay, so that is actually very important over here, contradicting with what we have done earlier, which is going to be for CH3 is electron donating group. Okay, so this is very important. Okay, now if I move on further, okay, of course, okay, I wrote over here mechanism. I think the mechanism is important for all, yeah. So but I want to discuss about the mechanism for Friedel-Crafts reaction, okay. But the same reaction, basically electrophilic substitution reaction. So for Friedel-Crafts reaction is more towards, okay, how do we put the branch, or how do we put adding a branch, okay, or side chain to the benzene. Okay, like if you have benzene, if I want something to go here, like for example CH 2CH3, so this is adding the side chain. So how do we add this side chain? By of course by using this reaction, what we call as Friedel-Crafts reaction. Friedel-Crafts reaction, there are two. Okay, one is going to be called as alkylation. Okay, because we are going to actually alkylation, we are going to add the alkyl groups, alkyl carbon and hydrogen groups. Yeah. So and we also have acylation. Acylation means of course acyl group. It means carbon double bond O. Okay, and then there will be halogens over there. So anyway, so there are two. Okay, so what is going to happen? So generally you need to understand, okay, the benzene is going to react with what? Okay, that is very important. So in order for this reaction to go from here to here, what am I going to react with? Okay, what am I going to react with? So basically you need to know that, okay, you are going to react with something that has CH2 CH3, CH2 CH3, but the additional thing that you need to know is it will react with something that has halogen, okay, which is going to be, there is Cl here. Okay, and then something that has this, so like for example they will react with C double bond O, CH2 CH3. So what is extra? Something that has Cl. Do remember, it is not limited only to Cl. It can also happen with Br. It can also happen with iodine as well. Okay, so but generally we use the Cl. The reason, I'll tell you what is the reason, because I think in the textbook one of the common catalysts that we use is going to be AlCl3. We have used AlCl3 before, okay, as a halogen carrier, but in this case, okay, AlCl3, are they going to be the halogen carrier? The answer is no, they are not halogen carriers, okay, because they are not going to carry the halogen, okay, into the benzene ring, okay, but they have some roles over there. So what is the role? Basically is like similar with the reaction earlier, which is going to be the nitrating mixture. Something will react with something to give you the electrophile. So in this case, what is going to happen is you are going to actually have you're going to try to produce electrophile. Okay, so if I actually put it down here, okay, maybe I try to do the mechanism for this. Okay, I try to draw the mechanism for this. So like for example, if I'm using AlCl3, okay, so AlCl3, they are going to react, okay, with this, okay, acyl chloride. We call it acyl chloride. So C double bond O, CH2, CH3, and then this one will be Cl. Okay, so what's going to happen? You are going to have, okay, generally if you want to show the, if they ask you to show the curly arrow, so generally this is, okay, the electron will go there towards the Cl. So the Cl will become negative and this one will be positive over here, partially positive. So the next is going to be the Cl, okay, they, after that they will go to AlCl3. So what's going to happen? You are going to get AlCl4 minus. AlCl4 minus. Okay. And then you are going to get, okay, C double bond O, CH2, CH3, and you have this plus. So this plus, okay, that's going to be your electrophile. Okay, that's going to be your electrophile. So what's going to happen next? Okay, it's quite simple. Maybe it looks complicated, but I think it's the same concept. Okay, the concept is basically you are going to have this benzene. Okay, and then when you have C double bond O, CH2, CH3, and this is plus. So what's going to happen if I want to actually draw the curly arrow diagram? So what's going to happen? The electron will move from here to here. Okay, so they are going to actually form, okay, a benzene, and then they are going to form an intermediate. So there is hydrogen here. From where suddenly the hydrogen come? They didn't come suddenly, they've been there all along. So you have carbon double bond O, CH2, CH3. So the next step is going to be, I made a mistake over here. This one, okay, is not going to be completed. Okay, it's going to be not stable. So they will have something like this. And the next step is going to be this electron, they will go here. And you are going to have the H plus coming out. Okay, and you are going to get, okay, I think to save time, you are going to get this, and you are going to get H plus. So what happens to this H plus? Okay, this H plus, again, they will join together with AlCl4 just now. Okay, so the AlCl4 minus plus H plus, they are going to get AlCl3 plus HCl. So this is the catalyst. So they are going to actually, the catalyst will come back again. Okay, so this mechanism and how to draw, I think you need to actually learn. Okay, very important. Okay, but I will move on, okay, to oxidation. Now, for the oxidation reaction, it's very simple. Any kind of alkyl benzene, so not limited to methyl benzene, everything. Okay, sir, we don't show the mechanism between Cl2 first. Okay, for the mechanism for Cl2, yes, you need to actually know the mechanism as well. Okay, we have already discussed about this as well. Okay, but I skip this part, Anita. Or are you asking some other thing, Anita? There are mechanism for this as well. Okay, so the mechanism for this one, okay, is going to be more towards when you have this Al or any catalyst or something like that, they are going to polarize. I think the additional concept over here, like, is it a must for us to write, sir? Actually, when they ask you to write, they will ask you draw the curly arrow diagram. It means they are very, they will ask you, the instruction will be very clear. So it's not like they suddenly ask you to, like when they ask you what is the reaction, then you just write the reaction only, like something like this. But when they ask the mechanism and they will say draw the curly arrow, then you need to actually draw in that way. But the difference of the mechanism of this and the previous one that I show is going to be, the difference is like for example, just now, if you look over here, the Cl, okay, the electron actually went from here to here. Okay, why? Because Cl is more electronegative. So we actually went over that. But it's going to be slightly different for this mechanism. Why? Because Cl2, they are not going to be the electronegativity, they are the same. Okay, if the electronegativity are the same, so what we need to do is there is going to be something what we call as AlCl3 or any of the halogen carriers. They are going to actually polarize the Cl2. It means polarize means they are going to actually induce some kind of a they will induce the Cl, okay, whereby one part of the Cl will actually have more electrons, something like van der Waals forces. So there is going to be delta negative and delta positive. Next, there's going to be heterolytic fission going to happen. Then the reaction is going to be the same. You are going to get AlCl4 and so on. So the difference is one is the first one is induced or polarizing. But here you do not need to polarize because the Cl is already there. You can read more about this. Please read after today's lesson. Yeah. Now, if I move on, okay, you can see that doesn't matter if it is going to be methyl benzene or any kind of alkyl benzene. When you oxidize, you are going to get a benzoic acid. So COOH, and you are going to get water. Okay, so balancing and so on, you can actually do it, no problem with that. Okay, so if you look over there, if you want to balance, it's going to be 3. But anyway, the conditions are going to be different. Okay, the condition is going to be, instead of just using acidified potassium manganate, the condition is going to be alkaline potassium manganate, and it's going to be after that only acidified with sulfuric acid dilute, and then they are going to be reflux. So slightly different than the normal oxidation. The normal oxidation, we just oxidize using potassium manganate, potassium dichromate, acidified, and then reflux. But in this case, the difference is going to be the alkaline, and then probably the dilute part over here. So you add sodium hydroxide, and then after that only you acidify. Why? It's not no need to know because it's not in your syllabus, so it's just the condition. This is how it's going to happen. Yeah, now still the same chapter. Okay, actually I prepared for 2 chapters. I don't think so we will be able to cover the 2 chapters based on the time that I see now, but anyway, okay, if we move on to phenol. Okay, phenol is generally a crystalline solid. Okay, it's a solid. Okay, it's going to be, the melting point is 43 degrees Celsius. You can read more why the melting point is higher, because it has hydrogen bonding. Okay, so melting point is higher, 43 degrees Celsius, so it's going to be solid. Okay, now for phenol, okay, what we need to know is we need to actually understand about the pKa, which one is more acidic. Like for example, phenol, water, and ethanol. Which one is more acidic? Okay, so maybe I'll try to ask someone over here. Shane, which one do you think is more acidic between these 3? Phenol, water, or ethanol?
Phenol.
Ethanol, you say more acidic. Actually,
Phenol.
phenol. Okay, phenol is more acidic. Good,
Phenol.
it's correct. Yeah. So why is that, Shane? Actually, there are 2 explanations given. Use any explanation to explain why phenol is more acidic.
Because hydrogen bond.
No, why you want to involve hydrogen bond? The moment you actually talk about hydrogen bonding, you should be only talking about boiling point and melting point, nothing to do with acidity. Okay, so when we are talking about bonding and so on, it's all towards hydrogen bond, the boiling point and melting point, nothing to do with acidity. So this one is has something to do with this. Like for example, if you have phenol, okay, there's OH, and then when they actually dissolve in water, so what's going to happen? You are going to get phenoxide ion, O minus over here, and then you are going to get the H plus over here. Generally, this is going to be happening. Yeah. So what is important over here that we need to take note? Maybe Charlton, do you have any idea why phenol is more acidic?
This one yang the negative spread.
Yes, very good. Okay, can you explain more about this? What will happen to this negative charge?
Spread throughout the molecule, so
Yes.
become less negative.
Yes. So this one, okay, the negative charge, or to be exact, the lone pair, okay, the lone pair, they will actually, the negative charge will actually spread, they will go into the ring, okay, they will go into the ring. So this negative charge is going to be spread out, okay, to all this carbon, okay, the ring. So when it actually spread out, okay, what happens? It will become less negative. So when they become less negative, what's going to happen is they are not going to be bonded very well with the H plus. Okay, they are not going to be bonded well with H plus. So when they are not bonded well with H plus, so it means there's a lot of H plus remaining. So if you have a lot of H plus remaining, so basically they are going to be acidic. Okay, there's another explanation to it. Okay, the another explanation is since the negative charges are being spread across all the carbons in the benzene, this makes this ion is called phenoxide ion. This phenoxide ion is going to be very stable. So they tend to form more stable. Generally, do remember in chemistry, they always like to form something that is stable. So this phenoxide ion is more stable. So when they are more stable, it means the position of the thing will be more towards to the right. It means they like to form the stable ion. If they form this stable ion, you are going to form more H plus. That makes it more acidic. So let's compare this, okay, with ethanol. Yeah. So when you talk about ethanol, C2H5OH, okay. So similar also C2H5O minus, and then you have H plus. But the difference over here is, okay, like what Charlton said. Okay, Charlton said that the negative, okay, for the phenoxide ion, they will be spread across equally. Okay, but here the problem is C2H5, okay, any alkyl groups, they are electron donating group. Okay, they donate electron. So when they donate electron, it means the electron is going to go there. So when they donate the electron, what happens is the negative charge, they are going to become more negative or less negative. Let me ask Jason over here. Jason? Is it going to be more negative or less negative?
Less negative.
Again, Jason, cannot hear you.
Less negative.
No, it will not become less negative, Jason, because you see, C2H5, okay, they are donating the electron. Okay, electrons are negative charge, and they this O has negative charge. So if you are donating electron, it means you are giving all the negative charges over there to the right. So generally, it is going to become more negative. Can you understand, Jason? So if you have more negative, it means that, okay, this H plus, they really like that. They love that. Why? Because, yeah, I want negative. I want electrons. So what the H plus do? They will go and combine. Okay, they will go and combine. And they will form, okay, this ethanol. Okay, when they form this ethanol, it means you do not have H plus, because H plus do not exist as H plus. They tend to actually exist in form of ethanol. So it means the position of the equilibrium is more towards the left over here. So it means they do not dissociate well, okay, to give you the H plus compared to phenol. So that actually gives you less H plus. So if you want to actually compare in terms of pKa, yeah, explanation I have already discussed with you. But if you want to compare in terms of pKa, if you have less pKa, it means that it is more acidic. So in this case, do remember pKa for phenol is lower or the lowest, okay, because that's going to be the less acidic, the most acidic phenol, and the pKa for ethanol is going to be the highest. Why? Because it's going to be less acidic. Ken Lavi. Can you follow, Lavi? Is it too much already?
So later this one will have the video and after that.
Yes. Okay. But again, today, because I think I'm recording this video, I will share it to you. But I think there will be some background noise. As I think you can hear my background noises. My son is actually studying beside me. But anyway, I will actually give you this. I will share to you this PDF. Okay, the one that I'm drawing over here. Even though it's messy, you can work out something. But again, do remember. Earlier, before we end the term, there is a video that we have done. I think it's not actually 1 hour. I think 20 minutes or something like that. I made 2 videos, I think. Please go and revise on that. If you want this video also, I will give it to you. Yeah. So again, this one is not complete. Okay. I'm just actually trying to recall all this from you. Yeah. So there's actually a lot of things that I want to actually teach you. Okay. But I don't think so I will be able to cover everything today. Okay. We only have 10 minutes. Okay, maybe tomorrow I will extend this tomorrow, which is maybe today we just cover the one topic, which is benzene. Tomorrow we will cover the carboxylic acid and derivative. Okay, but I really need you guys, okay, to go through. Maybe if you have this video, go through this video, go through the video that I shared to you before the holidays. Okay, and also go through the textbook. Yeah. uh, and then tomorrow we will actually do the carboxylic acid. I think the carboxylic acid part is not that much. Okay, but do remember we finished that carboxylic acid part in 3 lessons. Okay, so we were rushing for that as well. Okay, but please read on that as well today. So tomorrow when we actually go through this, and when I go through the carboxylic acid and derivative, basically whatever the 2 chapters that we have covered before the holidays, you can really have an idea, and then we can move on, okay, to the next part. Okay, the next part that we are going to move on is going to be this I think there's one more which is going to be still under organic. We call it as organic nitrogen compounds. Okay, so after we done the organic nitrogen compound, there's going to be polymerization. Let me check. Yeah, polymerization, and then after that, that's going to be analytical chemistry. So it means if we talk about organic chemistry, I think the moment you do I think polymerization, if you don't consider it as organic chemistry, I think we only have one more chapter to finish organic chemistry. It means, I hope you understand the organic chemistry. There are a lot of reaction. There's a lot of catalysts. There's a lot of mechanism, a lot of things to remember. Polymerization, maybe there are reactions, okay, but I think it's more easier to understand. So if you're thinking about, okay, organic chemistry, do we need to learn more? Okay, not really. Okay, we only have one more chapter on that. Okay, but this is the best time for you to actually do short notes and so on and try to recall everything. Yeah. So anyway, I'll share the screen again. Okay, hold on. This part, okay, I think I can actually skip this part, yeah, okay, because do remember phenol, okay, phenol, they can react with sodium hydroxide, okay, they will give you sodium phenoxide and water. Okay, no need for me to write the equation because it's the same as the textbook. Okay, so basically H and OH, so H2O, then you have this phenoxide, O minus and A plus. Okay, I'll just write. Okay, do remember the phenol also, okay, they react with sodium metal. Okay, they will give you phenoxide, okay, phenoxide ion, and then sodium phenoxide ion, okay, and then H2, hydrogen gas, okay, hydrogen gas. Do remember, I think I told you to relate this, okay, with your ethanol, okay. Please read, okay, ethanol can react with sodium, okay, but can ethanol react with sodium hydroxide? Okay, I think I already asked you earlier. Okay, but this one we leave it for tomorrow. Okay, but anyway, okay, if I just want to do a checking over here, let me see before the checking. Yeah, I think towards the end over here. Okay, so if I do a check over here, okay, like for example, which one is more readily react with Br2? Okay, so if I ask, is it going to be benzene or is it going to be phenol? Which one do you think will be more readily reacting? Jody? Benzene or phenol?
Phenol.
Phenol. So what is the reason?
The negative charge spread over that one.
No, actually, when we talk about the negative charge, yeah, the concept is correct, Jody. But I think when we talk about the negative charge being spread and so on, I think that is more suitable to show that whether it's going to be acidic or not. Yeah. But this one is more towards, I think the answer should be, okay, when you have phenol, okay, phenol is going to be bonded with OH. Okay. So the OH is going to be what we call as they are going to be electron donating group. Yeah. Do remember electron donating group in benzene. Yeah. So they donate the electron. Okay. So when they donate the electron, okay, what happens? Okay, or you can say that the electron they overlap, okay, with the pi bonding system. Yeah. So what happens is you are going to actually have this ring, okay, it's going to be having more electrons. Okay, instead of just having 6 electrons, you are going to have 7 electrons. Okay, more electrons. So when you have more electrons, okay, what happens is when you have electrophile, okay, electrophile they love electron. So if you have 6 electrons and 7 electrons, of course the electrophile will go to the part that has 7 electrons. So compared to benzene or phenol, electrophile loves to go towards phenol. Okay, they love to go towards phenol and react. So the reaction is going to be more readily reacting. The difference is like, for example, if you have like benzene, because I mentioned discuss about the difference. Okay, the difference is going to be if you have benzene, we need to, if you are using Br2, of course, you need to have halogen carriers. Okay, you need FeBr3. Okay, but for phenol, do we need halogen carriers? Okay, in this case, okay, do remember this is going to be very, very important for phenol. Okay, you do not need any halogen carriers. Okay, because the reason is this phenol, okay, they are going to be more readily available, so therefore, okay, you do not need any halogen carriers. Okay, it will just react. Okay, it will just react. And then like what is going to be hold on, yeah. Okay, like for example, this one just react. And do remember, for phenol, okay, they do not need any kind of heating. Okay, it just happens at room temperature. Okay, it happens at room temperature and then just simply react. So that is actually very important for phenol. You do not need to have any halogen carriers for this. Okay, but okay, if you look at the second part also, okay, reaction of phenol with Br2 will be similar to what? Okay, the question is it going to be similar to A or is it going to be similar to B? To answer this, maybe Janice, can you actually answer this? Phenol with Br2, okay, phenol with Br2, will it be similar with the mechanism for NO2, or mechanism wise is going to be similar, but is it going to be the similar with NO2, nitrobenzene or methyl benzene? Janice, 1 more minute left. Hurry up. Maybe Victoria, can you actually help out? The reaction of phenol with Br2, do you think similar to nitrobenzene or methylbenzene?
Is it NO2?
No. Do remember, okay, NO2, okay, is going to be electron withdrawing group. So if they are electron withdrawing group, okay, they are going to actually activate position number 135. Okay, so if you have this CH3, they are going to be electron donating group. Okay, so electron donating group, they will activate position 246. So phenol is also going to be electron donating group, the OH. So they are going to be more similar towards B. Okay, that's very important. Okay, so this is one of the things that I want to highlight. And then do remember, if you have this nitration, another reaction with nitration, apart from Br2, if you have nitration, normally nitration, we need to have this concentrated H2SO4, concentrated nitric acid, 55 degrees Celsius reflux. Okay, but because phenol is going to be more reactive, okay, so you just no need to actually have concentrated sulfuric acid. Dilute nitric acid is enough. Okay, and the reaction can actually give you this nitrobenzene. Okay, refer to the reaction. There are two products. Okay, basically why two products? Because this is going to be activating position number 2 and going to activate position number 4. Okay, so this one you can see from the textbook. We do have this reaction. If you have this concentrated nitric acid, okay, instead of using dilute nitric acid, you are going to get combination. What kind of combination? You are going to have this OH coming here, NO2 will come here, here, and here. So do remember, this is also 246 activating. Okay, so this is what we have learned in this chapter. Okay, this benzene. Yeah, so anyways, 11:31, you need to go to your another class. Okay, if you have question, you just can WhatsApp me. Okay, I will actually put this video for you as well. You can go through this. Okay, is that okay, guys?